Hi everyone, my name is ABHIJITH PA. I am a third year Electronics and Communication Engineering student from Government Engineering College Idukki. Today I am going to take a presentation on the topic Mathematical Analysis of PAM Signal. PAM. PAM means Pulse Amplitude Modulation. In pulse amplitude modulation, the amplitude of regularly spaced pulses are varied in proportion to the corresponding sample values of a continuous message signal. The pulse can be rectangular form or some other appropriate shape. In other words, pulse amplitude modulation, it is a signal modulation where the message information is enabled in the amplitude of a series of signal pulses. It is an analog pulse modulation scheme in which the amplitude of the train of carrier pulses are varied according to the sample value of the message signal. Pulse amplitude modulation as defined here is somewhat similar to natural sampling, where the message signal is multiplied by a periodic train of rectangular pulse. However, in natural sampling, the top of each modulated rectangular pulse varies with the message signal, whereas PAM is maintained flat. This figure is an illustration of the waveform of a PAM signal. The dashed curve in this figure depicts the waveform of a message signal m of t, and the sequence of amplitude modulated rectangular pulse shown as a solid lines represent the corresponding PAM signal s of t. There are two operations involved in the generation of a PAM signal. Number 1. Instantaneous sampling of the message signal m of t every ts seconds, where the sampling rate f of s equal to 1 by ts is chosen in accordance with the sampling theorem. Number 2. Lengthening the duration of each sample to obtain to some constant value t. In digital circuit technology, these two operations are jointly referred to as sample and hold. One important reason for intentionally lengthening the duration of each sample is to avoid the use of an excessive channel bandwidth. Since bandwidth is inversely proportional to pulse duration, however, care has to be exercised in how long we make the sample duration t of s, as the following analysis reveals. Let s of t denote the sequence of flat top pulses generated in the manner described in the figure. We may express the PAM signal as s of t equal to sigma n equal to minus infinity to infinity m of n of ts h of t minus n ts. Let's take it as equation number 1. In this equation, ts is the sampling period and m of n ts is the sample value of m of t obtained at time t equal to n ts. The h of t is a standard rectangular pulse of unit amplitude and duration t, defined as follows. H of t equal to 1 if 0 less than small t less than capital T. H of t equal to 1 by 2 if t equal to 0 and t equal to capital T. H of t equal to 0 in other conditions. By definition, the instantaneously sampled version of m of t is given by m delta of t equal to sigma n equal to minus infinity to infinity m of n ts delta of t minus n ts. Let's take this equation as equation number 3, where delta of t minus n ts is a time shifted delta function. Therefore, convolving m delta of t with the pulse h of t, we get m delta of t convolution h of t equal to integral minus infinity to infinity m delta tau h t minus tau d tau, which is equal to integral minus infinity to infinity sigma n equal to minus infinity to infinity m of n ts delta of tau minus n ts h of t minus tau d tau, which is then equal to sigma n equal to minus infinity to infinity m of n ts integral minus infinity to infinity delta tau minus n ts h of t minus tau d tau. In the figure A shows a rectangular pulse h of t, whereas figure B shows a spectrum of h of f made up of the magnitude modulus of h of f and phase argument h of f. Using the shifting property of the delta function, we thus obtain m delta of t convolution h of t equal to sigma n equal to minus infinity to infinity m of n ts h of t minus n ts. Let's take it as equation number 5. From equation number 1 and 5, which is equation s of t equal to sigma n equal to minus infinity to infinity m of n ts h of t minus n ts, and the equation m delta of t convolution h of t equal to sigma n equal to minus infinity to infinity m of n ts h of t minus n ts. It follows that the PAM signal S of t is mathematically equivalent to the convolution of m delta t. The instantaneously sampled version of m of t and the pulse h of t are shown by S of t equal to m delta of t convolution h of t. Let it be equation number 6. Taking the Fourier transform of both sides of equation number 6 and recognizing that the convolution of two time functions is transformed into the multiplication of their respective Fourier transforms, we get capital S of f equal to m delta of f capital H of f. It is equation number 7, where capital S of f equal to f of S of t and m delta of f equal to f of m delta of t and h of f equal to f of h of t. Adapting equation 3 to the problem at hand, we note that the Fourier transform of m delta of f is related to the Fourier transform of m of f of the original message signal m of t as follows. M delta of f equal to f of s sigma k equal to minus infinity to infinity m of f minus k fs. Let's take it as equation number 8, where f of s is the sampling rate. Therefore, the substitution of equation 8 into 7 yields s of f equal to fs sigma k equal to minus infinity to infinity capital M of f minus k fs capital H of f. It is equation number 9. Given a PAM signal S of t whose Fourier transform S of s is as defined in equation 9, how do we recover the original message signal m of t from it? As the first step in the reconstruction, we may pass S of t through a low pass filter whose frequency response is defined in figure. Here it is assumed that the message is limited to bandwidth W and the sampling rate f of s is larger than the Nyquist rate 2W. Then from equation 9, we find that the spectrum of resulting filter output is equal to capital M of f h of f. This output is equivalent to passing the original message signal m of t through another low pass filter of frequency response h of f. The flowchart represents the figure of system of recovering message signal m of t from PAM signal S of t. First, the PAM signal S of t is given to reconstruction filter. Then it is passed through equalizer and the message signal m of t obtained from this. From equation 2, we note that the Fourier transform of rectangular pulse h of t is given by capital H of f equal to t sin f of t exponential minus j pi f t, which is plotted in the figure. We see therefore that by using flat top samples to generate a PAM signal, we have introduced amplitude distortion as well as a delay of t by 2. This effect is rather similar to variation in transmission with frequency that is caused by the finite size of scanning aperture in television. Accordingly, the distortion caused by the use of pulse amplitude modulation to transmit an analog information bearing signal is referred to as aperture effect. This distortion may be corrected by connecting an equalizer in cascade with a low-pass reconstruction filter. The equalizer has the effect of decreasing the in-band loss of reconstruction filter as the frequency increases in such a manner as to compensate for the aperture effect. Ideally, the magnitude response of the equalizer is given by 1 by modulus of capital H of f, which is equal to 1 by t sin c f of t, which is equal to pi by f divided by sin pi f t. Let's take it as equation number 11. The amount of equalization needed in practice is usually small. Indeed, for a duty cycle t by ts less than or equal to 0.1, the amplitude distortion is less than 0.1%, in which case the need for equalization may be omitted together. The transmission of a PAM signal imposes rather strict requirements on magnitude and phase responses of the channel because of the relatively short duration of the transmitted pulses. Furthermore, the noise performance of a PAM signal can never be better than baseband signal transmission. Accordingly, we find that for transmission over long distances, PAM would be used only as means of a message processing for time division multiplexing, from which conversion to some other form of pulse modulation is subsequently made. So, here I am ending my presentation. Thank you all.